Welcome to a presentation on neoclassical physics. Neophysics has the most accurate theories of physics. We challenge you to disprove us. If not, we welcome you to join us and profit from the new science. In this presentation, we discuss about the least mystical way to explain Young's double slit experiment. Young's 1801 experiment was considered as the definitive proof of the wave nature of light. Because of this, Newton's corpuscular theory fell out of favor in 1800s. Here we show that we can very well explain the double slit experiment based on corpuscular theory of light. We can consider the light corpuscles as a rotating translating ring, somewhat like a wheel rolling on the ground. The direction of the angular momentum vector can be thought of as indicating the phase of the light corpuscle. Due to interaction with reflecting surfaces of the slits, this angular momentum vector may acquire a flipping motion. That is, the rotating ring may acquire complicated overturning movement. Different light particles may arrive with different orientation of the angular momentum vector at the photographic screen. The angular momenta follows cosine law of vector addition at the screen. This causes the observed interference fringe pattern. Since most of the latest precise photodetectors work on the principle of photoelectric effect, we shall take a brief look at that phenomena. At the core, photoelectric effect equation represents the transition from a bounded state to an unbounded state in a two-body system. The figure shows a two-body system with electrostatic forces. There is a massive positive charge with plus PE coulomb and a negative charge with minus E coulomb. From this two-body configuration, we get the conic section solutions. So the angular momentum of this system is conserved, and A is equal to m r square d theta by dt, where m is the mass of this electron, r is the radial distance between the nucleus and the electron, and theta is the angular displacement variable. So d theta by dt is the angular velocity. So A equals m r square d theta by dt. This quantity is conserved, and A is considered to be some non-zero value. A is greater than 0. The total energy of this system, that is the summation of the kinetic and the potential energy terms, can be written as this here. E is the total energy. E is equal to EB, where EB is some constant called the binding energy. EB minus 1 minus epsilon square, where epsilon is the eccentricity of the conic section solution. At, for example, for a circular solution, epsilon is equal to 0. And m divided by 2a square into PE, where PE is the charge on the nucleus, E is the charge on the electron, divided by 4 pi epsilon naught, where pi is a constant 3.14 something, and epsilon naught is the permittivity of free space. So E can be written as this expression here. So, and we also have another parameter called R naught, which is the semilattice rectum, which is proportional to A square. It does not have any dependence on energy, total energy E, but it is related to the angular momentum value, and it is proportional to A square. So this indicates the size of the conic section, size scale. So R naught is the semilattice rectum, and this equation R, the R equation here, shows the actual conic section solution. So R equals R naught by 1 minus epsilon cos theta. If the net energy E in this here is less than EB, then this two-body system has a bounded circular or elliptic orbit solution. If E is greater than or equal to EB, then the solution is unbounded. It will be either a parabolic or a hyperbolic solution. We can also note that the bounded orbits also correspond to the eccentricity value epsilon less than 1. And the unbounded trajectories have epsilon greater than or equal to 1. Suppose now we consider trajectories with epsilon greater than or equal to 1. So this is the angular momentum equation, this is the energy equation, and this is the actual conic section solution. R equals R naught by 1 minus epsilon cos theta. So at the angle when cos theta is equal to 1 by epsilon, if we put 1 by epsilon here, we get R equals R naught by 1 minus 1, which is R naught by 0, or R equals infinity. And for values of cos theta greater than 1 by epsilon, if it is greater than 1 by epsilon here, cos theta, then this solution is physically invalid, as R, which is the radial distance variable, becomes negative. When here cos theta is greater than 1 by epsilon, R becomes negative, which is physically invalid, the distance being negative. Hence, the valid solution only exists in the limit where cos theta is greater than or equal to minus 1 and less than 1 by epsilon. Realistically, cos theta can only asymptotically tend towards the value 1 by epsilon. So when cos theta is close to 1 by epsilon, we get d theta by dt equals 0. That is, the angular velocity becomes 0, and the radial velocity becomes a constant, which is given by this expression here. Dr by dt ultimately will become equals to plus or minus square root of epsilon square minus 1 into pe square by 4 pi epsilon naught a. So this is also the maximum radial velocity in this two-body configuration when epsilon is greater than or equal to 1. So this maximum radial velocity is also called the asymptotic radial velocity. And the asymptotic radial velocity dr by dt is related to the energy as shown here. So in this energy equation seen earlier, we can just replace this second part of the equation by kinetic energy. Since epsilon square is greater than 1, this 1 minus epsilon square becomes negative, and so this becomes an addition, minus of minus, Eb plus epsilon square minus 1 into this expression. So when epsilon is greater than or equal to 1, we can convert this equation into this form, where Eb plus half m dr by dt square, where dr by dt represents the maximum radial velocity or the asymptotic radial velocity. So this is valid only when epsilon is greater than or equal to 1 and cos theta is very close to 1 by epsilon, not exceeding 1 by epsilon. So we know if epsilon is less than 1, or when the total energy is less than the binding energy, E is less than Eb, we get bounded orbits. And according to Bohr's analysis, these bounded orbits will have discrete energy states. So, and we can write these discrete energy states as shown here. So in case epsilon is less than 1, we can replace this expression E equals Eb minus 1 minus epsilon, this complicated looking equation, by just E equals Eb minus E naught by n square, where n is a natural number, n equals 1, 2, 3 up to infinity. So these are the allowed discrete energy states according to Bohr, where E naught is a constant equivalent to this with A equals h bar. So if we put epsilon equals 0 and A equals h bar, we get this value E naught. And E is Eb minus E naught by n square. And the lowest allowed energy state, that is the energy state when angular momentum is just h bar, A equals h bar. So the lowest allowed energy state is when n equals 1 here. So as n increases its value, this the total energy increases, the total energy increases from Eb minus E naught to Eb. So therefore the lowest allowed energy state of this equation is n equals 1, and then it is E equals, at that point E equals Eb minus E naught. And we know the final state is unbounded and it is related to the asymptotic radial velocity. So we saw this is the final state, which is the state where epsilon is greater than or equal to 1, which will be reached after the transition. So EF equals Eb plus half m dr by dt square, where this is the maximum radial velocity. And the initial state we described here at n equals 1 is EI equals Eb minus E naught. So this is the initial state, this is the final energy state. and the difference between them is delta E. So delta E equals EF minus EF, final state minus initial state, will be just E naught plus half m dr by dt square max, where this is the maximum radial velocity. So the energy change between the final and the initial velocity is just E naught plus half m dr by dt square. And we can see from this above equation that the photoelectric effect equation, or the idea, Einstein's photoelectric effect idea, which is written here, h nu equals h nu naught plus half mv square. This can be exactly written in terms of the two-body system equation here, E naught plus half m dr by dt square. So h nu naught is equivalent to equivalent to E naught. Half m v square is equivalent to this asymptotic radial velocity at cos theta tending to 1 by epsilon, and h nu is the delta E, which is the change in the energy of the system. So this h nu equals h nu naught plus half mv square, which is Einstein's photoelectric effect equation. It can be written in terms of this two-body system when epsilon is greater than or equal to 1. And this can be interpreted as an equation showing a transition between the lowest energy state, n equals 1, that is the initial state, which is the bounded state, to an unbounded state where n equals infinity, and beyond this bounded state, which is n equals infinity plus, or which becomes where n might become an imaginary number, because in this case E equals EB minus E naught by n square. As long as n is some positive natural number, it cannot, the value of E cannot exceed EB. So if it has to become EB plus something, then the value of n should become imaginary. So which is like the beyond unbounded state. So unbounded state is just n equals infinity, and we have states defined even after that when energy E becomes greater than EB. So these are the transitions from the initial state EB minus E naught to a state which is beyond the unbounded state, which is beyond n equals infinity. So it is also possible that instead of an individual electron, a group of n electrons are interacting with the light in unison. So here this equation proposed by Einstein just shows an interaction of one photon with one electron. But it is possible that a group of n electrons are interacting in unison with the light. That is, if there is a group of n electrons which are acting together, then we need n photons or n step activation to make transition between the lowest energy state, lowest energy level bounded state, to an unbounded state and beyond for all these n electrons. That is, till it gets n photons, it keeps collecting the photons. As soon as it reaches n, all these n electrons in this group can reach the unbounded state. So this is additive. If there is a group of n electrons, they'll keep adding up to n photons before they all become free electrons simultaneously. And here it is just an interaction showing with one electron. And if we want to see this in terms of a group of n electrons, which is multiplied by this big N on both LHS and RHS. So instead of acting photoelectric effect, instead of being a single electron, single photon phenomena, it can be a group phenomena, or a phenomena observed in a collection of items. So these n electron groups can behave as one object interacting with these light photons. So since there are n electrons, it will need n photons in total to make them go from the lowest energy state to highest energy state, or beyond unbounded state. So we can just change this h nu equation to nh nu equals nh nu naught plus n into half mv square. This is the group behavior. So let us now look at the more in detail about the structure of light particles itself. In the discussion about limitations of Bohr's model, We had already discussed that the photons may have a ring-like structure with discrete angular momentum like h bar, 2h bar, 3h bar, and so on. So it will have discrete angular momentum, and because it is a ring which is rotating, so it will have an angular momentum, but it is discrete. Let us consider that the normal type of photons have only angular momentum h bar. So that is they don't have 2h bar, 3h bar, etc. It is a normal photon which has just angular momentum h bar. And the direction of this angular momentum h bar is shown by the blue arrow. The translation motion shown in this red arrow, it can be in any direction. It need not be always in this orientation with respect to the angular momentum. It can be oriented in any direction, x, y, z axis. So in order to get the interference pattern, we need a source of light which is coherent and monochromatic. That is, the light coming out of the source should have one particular frequency nu, which is the meaning of monochromatic, and the waves or the light particles should be emitted with a particular phase phi from the source, which is the meaning of coherent. So all the particles emitted by this light source, they should be emitted with a particular phase from the source. So then they can be called as coherent. So not only the rate of the frequency, the rate of oscillation or the rate of spinning should be the same. The phase or the orientation of the spin must also be maintained by the source. So that is the meaning of coherent and monochromatic. So that is, if we consider that these four photons here, that is photon 1, photon 2, photon 3 and photon 4, were emitted at different times from the source along a particular ray direction, and we take a snapshot at an instant of time, they all have same phase. That is, all these blue arrows are parallel to each other, aligned with one another. So that is the meaning of coherent. So if all these photons emitted from this source, they have all these different photons, we take a snapshot and observe all these photons together, they will all have their angular momentum orientation aligned. All these blue arrows will be parallel to each other. So that is the meaning of coherent signal. And that will be the same observation we will make if we stitch together snapshots of a particular photon. Suppose there was one photon which is moving from this place to this place. At t equals 0, the photon was here. At t equals 1, the photon was here. At t equals 2, the photon was here. And at t equals 3, the photon was here. And if we glue together all these 4 snapshots taken at these 4 different time instants, then also we will find the same observation, that all these blue arrows, angular momentum vector direction, are aligned to one another, both either watching one single photon translating or watching several photons at the same time instant. So this means these signals are coherent. That is, they have the same rate at which they are spinning, the ring is spinning, and their angular momentum directions are all aligned. So these flipping angular momentum direction, that is, at one place the angular momentum is directed up, at this place the angular momentum direction is down, it's up here, and then again it's down here. So if there is a flipping angular momentum like this, then this will be an example of a monochromatic light. It can have the same frequency, but they are not coherent because these angular momentum directions are not the same. So any variation from, if they are not parallel, no matter what, they have to be 180 degree off. No matter what the angular differences happens, it becomes incoherent or it is not coherent. For coherent, all these angular momentum directions have to be parallel. So consider a coherent monochromatic source of light emitting photons in various directions. So it's going in some direction here, it's going straight, and it's going down like this. So it's sending out photons in various directions, but all their spin rates and the spin orientations are the same. So they are spinning at the same rate, that is monochromatic, and their spin direction shown by this blue arrow, they are all aligned and they are all parallel to each other, so they are coherent. Suppose the rays from the source are intercepted by the double slit arrangement. So here it's a double slit. There are two gaps here for the light to go, and this is some metal or some blockage. The light cannot pass through these black region, and this white region is the two slits in this embedded inside this black surface. So the light is intercepted by this double slit arrangement. The rays hitting on the different portions of the slit edge surface, that is here, or a surface like this, slit edge surface like this, the rays hitting on the different portion of the slit edge surface will be reflected at different appropriate angles according to the law of reflection. But we assume that they all acquire a flipping motion. All these photons or the light particles which hit this slit surfaces, edge surfaces, they acquire a flipping motion after getting reflected at the slit edges. And the rate of flipping is assumed to be same as the spinning frequency of the ring. So if the spinning frequency of the ring was nu, this flipping frequency will also be nu. In the example, we have shown that the ray emerging from the upper slit, in this example, the ray emerging from the upper slit has a smaller travel distance. Hence, it undergoes lower number of flips, because the rate of flips is the same for both the objects. Since it is traveling a shorter distance, it will have a lower number of flips as compared to the ray emerging from the lower slit. So if we assume if we consider the particles coming at this place on the screen, it is at a shorter distance from this slit and a longer distance from this slit, so the number of flips will also be different. So because the top slit, this upper slit is closer, the photons coming from there or the light particles coming from there will have lower number of flips. Hence, when the distances are unequal, the photons arrive at the screen with different phase angles. So here we have shown the phase angle difference as 180. This is oriented up and this is oriented down. But it can arrive at any phase angle, 0 to 180. So that is basically the photons arriving at the screen or the photographic plate. They would have traveled different distances from the two slits depending on where on the screen they hit. So, and depending on that, the number of flips will be decided. Suppose screen or the photographic plate consists of a group of n electrons acting in unison. That is like shown by these gray rings here and the gray rings here. So these are a bunch of n electrons which are at the screen, and they are the ones which will interact with this impinging photons. So they are all at the lowest possible energy and angular momentum level. So all the electrons in this group, n group electrons, they are at the lowest angular momentum and lowest energy level. So that is the total angular momentum of the n electron group is a old. That is what it possesses initially. A old is nh bar, because n is the number of electrons in the group and h bar is the angular momentum of each electron. So a old is nh bar, and the total energy of the n electron group is E old equals n times Eb minus E naught. This is the lowest energy. So total energy of this n electron system is n into Eb minus E naught. In this case, a photon is accepted when they are in this lowest energy and angular momentum state. In this case, a photon is accepted if and only if the relative phase difference angle, that is phi, should be 0. That is, the phase difference angle phi between the present angular momentum of the electron. So this light blue line shows the direction of the angular momentum of the electrons. This is the present angular momentum of the electron, and the phase of the incoming photon, if they are the same or the phase difference is 0. So basically in this, these gray photons are aligned with the angular momentum vector of the electrons, but this is having a misalignment. This is 180 degree off, and so the difference between this downward arrow and this upward light blue line is 180 degrees, whereas the phase difference between this gray photon with upward blue arrow and all these electrons with upward light blue arrow is 0, because they are aligned, their angular momentum are aligned. So in case when this bunch of electrons, this group of n electrons are at the lowest energy and angular momentum state, they can only interact with the photons which have the same angular momentum sense as themselves, that is angular momentum parallel, like these gray particles here. See, these gray electrons will only interact with these gray photons here. So that is the meaning of it, at the lowest angular momentum and energy level. So basically, because this group of electrons with angular momentum here are aligned with the gray photons that are coming. So the phase difference between this gray and the black photon at this place is 180 degree, like we saw in the previous slide. And the phase difference between this gray photon and this black photon is say 130 degree in this example. So these are the kinds of photons that are coming and falling on the screen. But the screen, suppose, has a group here at this place, as a group of electrons which is only aligned with these gray photons. They are parallel to these gray photons. So that's why the electrons are also shown as these gray rings. So they can absorb these gray photons, and they will either reject, that is either reflect or transmit these black photons when they are in the lowest energy and angular momentum state. So basically in the example that we have shown here, the electron group at the screen is aligned with the angular momentum of the gray photons originating from the upper slit. So the grays are being considered as originating from the upper slit. Like here, these are the gray ones, they are coming from the upper slit, and these are the black ones, these are coming from the lower slit from onto the screen. So in this example, the electron group at the screen is aligned with these gray photons originating from the upper slit, and therefore if those photons arrive at these group of electrons, they will be absorbed. The angular momentum and energy content of the n electron group will then change as shown below. That is, A old was the total angular momentum of this group, which was nh bar plus h bar. H bar is the new angular momentum of the new photon coming in. So A old plus h bar is just n plus 1 h bar. Remember, this happens only when there is alignment between the incoming photon and the electron angular momentum. So these two are parallel, the light blue line and this both these blue lines are aligned. So that's why it just happens to be simple addition, A old plus h bar, n plus 1 h bar, and the energy state changes from E old plus h nu. So this was the whatever the energy that was there before interacting with the photon. So once this photon with the parallel angular momentum is absorbed, its angular momentum rises by 1 unit h bar, and its and the total energy of this group of electrons increases by h nu. So, or n into Eb minus E naught plus h nu. However, in contrast, if the black photons from these lower slit, which are not aligned with the electron group angular momentum at the screen, if these black photons were to arrive first, it will be rejected at the screen or by this n group electrons. it will be either reflected back or transmitted through the system, because they are misaligned, and these group of electrons are at their lowest energy and angular momentum state. But if the electron group were at an higher energy and angular momentum level, then the energy from the misaligned photons, from even these black photons, they can also be absorbed by the electron group, by these gray photons. That is, as long as this A old, or the total angular momentum possessed by this group of n electrons, is greater than or equal to n plus 1 h bar, and its total energy E old is greater than or equal to n plus 1 into EB minus E naught. So if the total energy is greater than the level like n plus 1 terms, not in the lowest energy and angular momentum state, if it is higher than that, then the impinging photons with different phase angle than that of the electron group. So here they are misaligned, they are not parallel. Here also they are misaligned. Even these kinds of photons will be absorbed, and the A vector, the angular momentum vectors, get added according to the cosine law. So if there is a phase difference of phi of 180 degree here, or phi is 130 degree, it doesn't matter, they all get added according to this cosine law, vector addition. So if A old was the initial total angular momentum of this group of electrons, and h bar is the angular momentum of the incoming photon, and these two are aligned at some angle cos phi, there is a phase difference between the incoming photons and the electron group. So then this is how we add up the angular momentum vectors according to the cosine law. So this can be done only if and only if the total amount A old of this n electron system is greater than n plus 1 h bar, and the energy is greater than this value, n plus 1 into EB minus E naught. So under this condition, we can add up like this vectorially. And in this case, the E is defined as E is E old plus the difference between the new angular momentum and the old angular momentum. So this is the extra angular momentum that this system, this n electron system got, and the total energy added will be a function of that difference between the new angular momentum A minus the old angular momentum A old. So energy addition goes as this, and the angular momentum is added like this vectorially according to the cosine law addition. And here note that nu has to be greater than this threshold frequency. Nu is greater than or equal to nu naught. So if the black photons arrive first, they can also be absorbed provided the electron group has the right orientation. So the photons which have the parallel orientation to the group of electrons, they are the ones which will be absorbed first. All the others will be reflected or transmitted. So once the first photon is absorbed, and this system, n electron system, goes to a higher energy and angular momentum state, then they can interact with photons with different phase angle. So at the first step, this is what happens. This is just like the direct discrete addition, almost like Bohr type. And if the gray photons arrive next, or this is the black which was aligned and this was absorbed, and if the gray photons arrive next, then its angular momentum addition with the electron group follows classical vector addition and loses its discrete character. So it is not discrete addition like Bohr type additions anymore. This is like the discrete addition, and here it is more classical type. It is not discrete anymore. And but even then this becomes discrete at two values. At phi equals 0, it just becomes this, and at phi equals 180, it becomes opposite of this. It becomes n minus 1 h bar and minus h, and it gives out energy when phi equals 180. So that is, the angular momentum of the electron group no longer varies in discrete units of h bar, and the quantity of absorbed or emitted energy depends on the difference between the old and new angular momentum value of the electron group. So we saw this earlier. So under the condition where A old is greater than n plus 1 h bar, we can add this up in this fashion, in a classical vector addition fashion. And the total energy absorbed during this situation is just dependent on the difference of the angular momentum between the two states. Suppose we have a series of photons impinging on the electron group. So this this is the electron group, and these are the series of photons impinging on the electron group, such that their relative phase angles with respect to the electron group is 0, phi, 0, phi, and so on. So this photon, the first photon is parallel to it, the second photon is aligned at some phase difference angle phi, and the third one is the black photon, which is aligned with the group, the fourth is not aligned, and so on. So there is a series, we get 0, phi, 0, phi, 0, phi with this group. And we use these procedures we discussed here. Therefore, for the first photon, if it is in parallel, we apply this procedure, this discrete addition that we described earlier. Therefore, after applying this top procedure in the first step, we do repeated calculation of the second procedure at the bottom for all this. So for the first one, we apply this, and for all the others which follow this first photon in this series 0, 5, 0, 5, 0, 5, we can just repeatedly apply this second procedure at the bottom. However, if phi equals 0 here in this vector addition, then it will just become repeated application of the first procedure, because at phi equals 0, this becomes same as this, because it's phi equals 0 here. So either if phi is 0 or phi is different, when we have a series of 0, phi, 0, phi, 0, phi, after following this procedure at the first step, we do repeated application of this procedure at the second step, we get a table of values. Basically, we can write out this energy collected at each angle phi, for each angle phi. So this can be 20 degree, 30 degree, 50 degree, or whatever. So if this group of electron is collecting photons of different phase difference angles, then we can write out the energy collected at each different phi after each step, after each absorption of the photon, as shown in this table. That is, this is a group of two electrons which are interacting with the impinging photons. So these are the phi angles. So for example, at phi equals 0, the series of photons that the electron group is receiving are all parallel. It's like 0, 0, 0, 0. All parallel photons are coming towards the electron. So all of them are just absorbed straight up. So if 2 photons come, 2 h nu energy is absorbed. If 3 photons come, 3 h nu is absorbed. If 4 photons come, 4 h nu is absorbed. So at phi equals 0, whatever the number of photons is received at this place will be absorbed, because all of them are parallel to the n electron group. So after receiving 2 photons, this column pH equals 2, after receiving 2 photons, the only in places where the phase difference angle is 0, so in places on the screen where the phase difference angle is 0, the group of 2 electrons can be released wherever these only in those places the group of 2 electrons can be released at phi equals 0, because they receive the whole total 2 h nu amount of energy. But other places we need more than 2 photons to release the electrons. So for example, after receiving 2 photons at phi equals 0, it has received the whole 2 h nu, but at 5 degree it has received only 1.99 h nu. At 10.1 it has received only 1.988, and for example at 135 degree it has received only 0.4 h nu. Of the total 2 h nu energy falling on that place, only 0.399 has been absorbed by the system at this place where the phase difference angle is 135. So we can continue the vector addition process, that is the process described here. We can continue this process to know the number of photons required to release 2 electrons at each of this phi value. For example, basically at 135, let us consider at 135, when the 2 photons fall on the system, only this much is collected. When the third photon falls, this is the total energy of the system. When the fourth photon falls, it becomes this, and so on. So only when it has received total 7 photons, its energy becomes 2.156, and since it is greater than 2, now it is ready to give up 2 electrons, or 2 electrons in there have received more than 2 h nu, absorbed 2 h nu amount of energy, and they are ready to go from a bounded state or the low energy state to an unbounded state or beyond that. So the place associated with phi equals 90 degrees can release the 2 electrons only after receiving 3 photons. So after receiving 3 photons at phi equals 90, the total energy absorbed by the electron group, the 2 electron group, is 2.16228. So since it is greater than 2 h nu, it's ready to give off the 2 electrons. And a place like associated with phi equals 120 degrees needs 5 photons to release the 2 electrons here, because only after receiving 5 photons its energy level exceeds 2 h nu. And we saw at 135 it needs 7 photons to exceed the energy 2 h nu. So at different angles, as the value of the angle increases, phase difference angle increases, it needs more and more photons to release 2 electrons from this group. We can also graphically notice that each of these columns, like the columns under pH equals 3, pH equals 4, or number of photons, pH equals 5, and so on, each of these columns nearly have a cos square phi by 2 variation. So this is phi, and the variation we observe on these columns is cos square phi by 2 with increasing phi. So this is the graphical version of the table we saw in the previous slide. The left panel shows the actual number of photons collected or absorbed at each phase difference angle phi. When this black line shows 4 photons were impinging on the surface, red line shows 10 photons impinging, green line shows 20 photons impinging, and blue line shows 30 photons are impinging or received at the surface. So if 30 photons are received at phase angle phi, all the 30 is absorbed because all of them are parallel to the electron angular momentum. But if the same 30 photons that are falling, only about 20 are absorbed at phase difference angle 80. So at 80 degrees, if there are 30 photons falling, only 20 of them will be absorbed, and the energy level will increase only according to this 20 h nu, while the rest 10 are rejected. They are either transmitted or reflected back. So these different colored line shows of the total number of photons falling. For example, here there are 10 photons falling. How much of them is absorbed by the photographic plate with different phase angles associated with it. So as the phase angle increases, as the phase angle becomes 180, almost no photon is absorbed. So if we normalize this, we get this these graphs. That is, if we normalize this blue line divided by the number of photons received. So if we divide this values of this blue line by 30, or this divide this green line values by 20, or this red line values by 10, we get these normalized lines here. So this is called the ratio of energy collected to energy received as input, or energy impinging. So this ratio EC by EI is nothing but these blue line normalized by the number of photons received. That is, blue line is receiving 30 photons, but at 80 it's only absorbing 20 photons, so 20 by 30 will become 0.6 something here. So we normalize each of these lines by the number of photons received to get the lines plotted here. And the cyan line in this right panel is the cos square phi by 2 curve, which is just the cos square phi by 2 depending on these phase angles. And the ratios of the energy collected, EC, to the energy received as input, EI. This is the collected, this is the actual received, EC by EI. So these ratios are plotted here after two steps. That is, this is a group 2 electron after receiving 2 photons, or after 2 steps. This black line shows the graph of EC by EI. This there is one red line here which shows the EC by EI ratio after 4 steps. There's a green line here which shows the EC by EI ratio after 20 steps, and there is a blue line here which shows the EC by EI ratio after 42 steps. And as we see, as the number of steps increases, this graph becomes closer and closer to the cos square phi by 2 curve. So basically, with increasing step size, or with increasing the number of photons received at that place, or with the larger electron group size, if we start with, here we have considered 2 electron group. If we start with a 20 electron group, that is n electron where n equals 20. So if we start with that group, either with increasing step size or with the large electron group size, the ratio of EC by EI, this ratio becomes almost exactly same as the cos square phi by 2 curve. So we can say this is the ideal case behavior, cos square phi by 2. All this in the limiting case where there are a lot of photon interactions involved, or a lot of electrons in the electron group, then the variation, the energy absorbed variation according at different phase angle become cos square phi by 2. And this is consistent with the intensity variation calculated by Thomas Young in 1801. Basically, this means that when the phase difference is 0, all the 100% energy is absorbed. And when the phase difference is 40, the less is absorbed according to cos square of 40 by 2, and at 80 it's even less. And so at 180, cos phi by 2 is 90, cos 90 is 0. So at when the phase difference is 180 degree, no photons, no energy is absorbed. So therefore EC by EI ratio is 0. So whatever we calculated using our procedure is consistent with the experimental observation and the theoretical calculation done by Thomas Young in 1801. So this is a table for the group of 20 electrons, n equals 20, interacting with the impinging photons. So this is the group of electrons after receiving 20 photons, after receiving 21 photons, after receiving 22 photons. So these columns represent the different number of photons received, and this is phi at different angles. So the energy collected at different phi by the 20 electron group and the number of photons incident are shown in this table. For example, at phi equals 10.08 degrees, of the 20 impinging photons with total energy 20 h nu, only 19.8508 at 10 degrees, 10 phi, only 19.8508 h nu is absorbed or collected. And of the 21 impinging photons with total energy 21 h nu, only 20.8508 h nu is collected. And once this collected energy exceeds 20 h nu, which is the number of electrons in the group, so once it's exceed n h nu or 20 h nu, all the 20 electrons in the group can become unbounded simultaneously. So it was a group of 20 electrons, they absorbed 20 h nu, they collected all these photons over some steps. Here it was 21 steps, but here if it was at 45 degree, it will take 24 steps to collect 20 h nu. So whatever the number of steps, as soon as it collects 20 h nu, the electrons in that 20 electron group are ready to go from a bounded state to an unbounded state and beyond simultaneously. And also we can observe these columns with the group 20 electrons are much closer, these columnar values are much closer to the cos square 5/2 variation than the 2 electron group values. But for an n electron group, if the energy collected at some step is n plus del h nu, for example here at at phi equals 10, at 10.08 degrees, we know after it receives 21 photons, it will be able to collect 20.8508 photons, or energy equivalent to this 20.85. So here n equals 20 because this is the number of electrons in the group, and there is a remainder 0.8508 which corresponds to this del. So the question is, and this del is always between 0 and 1. So the question is, how will this excess energy delta h nu, this remainder 0.8508, how will that be accounted for? So all the 20 electrons that are going from the bounded to unbounded state, they can consume this 20 h nu according to the photoelectric effect equation. This, it will become the, or this, if there is a group. This is for the individual electron. If there is a group of 20 electrons, n equals 20 h nu will follow this, but there will be a remainder 0.8508. What will happen to that? So because if the incoming frequency is new, then it has to satisfy this photoelectric effect equation, and so the Vmax cannot exceed due to excess contribution from h nu. So basically we cannot add this remainder here into this equation, this photoelectric equation, because if there is some n plus delta here, then Vmax increases, and that is not allowed, because at this particular frequency nu, the maximum velocity, observed velocity of these electrons has been observed to be given by this. This gives the Vmax square. So if there is an addition of energy here, n plus del, then Vmax increases, and that is not allowed, because at this particular nu, there is a particular Vmax. Experimentally we have seen that. So this remainder 20.8508 of the 0.8508 cannot go into this photoelectric effect. Only 20 can go, 20 h nu can go here, and then it can change the state of 20 group electrons from the lowest energy state to unbounded state, but 0.8508 still remains. And since this cannot be, this excess delta h nu cannot be given to these electrons going off in the photoelectric effect, this excess delta h nu must remain in the material when the n electron group becomes unbounded. So even when the n electron group becomes unbounded, this remainder energy 0.8508 must remain within the material. This can be realized by considering smaller electron groups, say of the size 2 or 4 electron groups, embedded in a larger scale structure like 20 or 200 electron groups. So there are smaller electron groups embedded in a larger electron group. And in that case, for example, assume that there is a smaller group of 2 electron size, or X electron here in the first layer here, interacts, this is the layer which interacts with the incoming light from the 2 slits. So these 2 wavy lines represent the light coming from the 2 different slits, and these first layer electrons are the ones which interact with it. But it is nevertheless connected to this whole 20 group of electrons like in this stack, but these are the ones which will interact with the incoming photons. So this smaller group of 2 electrons, or X electrons, they get emitted out with exact energy corresponding to 2 h nu or hex h nu. So once the energy is collected, these are the ones which will be emitted out as the photoelectric effect. from the 20 electron systems. So the remaining 18 remains here, these electrons. Only these two get emitted out once the energy is collected. So these are the smaller X group of electrons in a larger N group of electrons, or these two electron groups embedded in a 20 electron group. So in this case, if these two electrons go off, that will carry 2 h nu, and the remaining delta h nu joules stays in this larger electron group. So this delta h nu will be distributed through this 20 electron large group, and it gets added smoothly and maintains the cos square 5/2 statistics. Only these two electrons go off with the exact energy related with the photoelectric effect. Rest of the remainder stays in this larger group, getting added smoothly and maintaining the cos square 5/2 statistics. So the smaller electron group, which was emitted out from its low energy state, will soon be replaced by new electrons falling from the higher energy state. So it will be having some higher energy state electrons surrounding it. So as soon as there is a void or a gap, because these two electrons are emitted out due to photoelectric effect, the higher energy electrons will jump and fill this space. This is especially true when this photographic plate is connected to the electron bath. Negative charge is connected to the negative charge. So thus steady state like value of the larger group N electron is maintained. So periodically the X electrons can go out due to photoelectric effect, and another X electrons from a higher energy level can fill that space. So this X is in constant cycle, but the total number of electrons N in the larger group, that is maintained more or less constant, steady value of N electron. And only a part of that larger electron group will be emitted at each emission. So basically what happens is, for example, at 10 degrees, after receiving 3 photons, only 2.99 is observed. After receiving 5 photons, 4.98 is observed. And after receiving 7 photons, only 6.96 is observed. There is a gap. So once it reaches this 2.99, we can get 2 electrons from this 3 photon inputs. So the remainder 0.99 units will remain in the larger group and will be added. And after 5 photons, we can get total 4 electrons. So 2 we have already got. We can get 2 more electrons, and there will be a remainder 0.98. And after inputting 7 photons at this place with phase difference 10 degrees, we can get 6 electrons out, free electrons, and 0.96 energy will still remain within the system. So like this, smoothly this continues and maintains the cos square 5/2 statistics. So according to the corpuscular theory, the number of photons required at a particular phi phase difference angle to release X electrons. So at a particular phi phase difference angle, if we want X electrons out from that place, how many photons should be impinging on that place? So the answer is X by cos square 5/2. So by simply counting so this is always greater than or equal to X. Only at phi equals 0 we get this as just X, and for all other values of phi greater than 0, this value X by cos square 5/2 will be greater than X. So by simply counting or detecting only the electrons emitted due to the photoelectric effect, we may not be able to know total how many electrons were actually arrived at that place on the photographic plate, because of the total X by cos square 5/2 photons coming, only X electrons are released if the phase difference angle is phi. So just by noticing X electrons, we cannot know what was X by cos square 5/2 number of photons that came onto the plate, because in effect the electron group is integrating the angular momentum value of the incoming light particles. It is not integrating energy. So since it is not integrating energy, it is not straightforward mapping between x electrons and x photons. So we have to be careful there in the interpretation. So that is at a place where the phase difference angle is 180 degrees. Suppose one photon is coming parallel to the electron group, to the parallel to the angular momentum of the electron group, and another photon is coming at 180 degree. It is anti-parallel to the electron group. So at that place, it does not mean that no light comes to that place. Rather, corpuscles with alternate angular momentum vector arrive. That is a series like phi equals 0, 180, 0, 180. So these are the incoming photon series. Since it is coming alternate 0, 180, 0, 180, these are the kinds of angular momentum we are getting, thus maintaining the net angular momentum of that place 0. So if this we add as plus 1, this will be minus 1, plus 1, minus 1, a series of 1, plus 1, minus 1. The net angular momentum after an even number of steps will be definitely 0. Or even otherwise, even in the odd step, the angular momentum will be extremely low. So the smaller electron group with group size at least 2 or greater than or equal to 2, they can take up the energy or absorb the energy when phi equals 0 or the phase difference angle is 0, and they will release it back when phi equals 180. So when the parallel photon comes, they absorb the energy. When the anti-parallel photon or the photon with 180 degree difference between the angular momentum vector, when that comes, that is not only reflected back, the older energy that was absorbed is also released. So these two photons are released. So when so if the system is at A equals NH and E equals 0, one photon comes which is aligned with this NH. It goes to N plus 1 H bar and E becomes EH nu. So H nu is absorbed. But when 180 comes, it is not only reflected back, the one which was absorbed earlier, which is also given back. So this H nu which was absorbed earlier, it is also given back, and the energy and angular momentum of this electron group, it comes back to the original state. So when phi equals 0, it absorbs, goes to the higher energy state, and when phi equals 180, it actually gives up the older energy that it had absorbed and comes back to the original lower energy state, lower energy and angular momentum. So effectively this place with phi equals 180 degree is not actually collecting the energy impinging on it, and it does not mean that no energy is falling at that place in the first place. So the usual interpretation of this is that no photon is actually falling on the photographic plate at those particular places, but according to the corpuscular theory, it means that the photons are falling. There are a lot of photons falling, but since they have opposite angular momentum orientation, the angular momentum is getting cancelled. So the integrated angular momentum at that place is 0, and also therefore the no energy is being absorbed. Whatever the energy that was absorbed when phi is 0 is being given up when phi equals 180. So the overall there is no actual energy collection. And this is also the least mystical way to explain Young's double slit experiment possibly. So we stop here. Thank you. If you want to understand the concepts of physics in the clearest way, regardless of the concerns about scoring high marks in exams, please visit neophysics.com. Thank you.